This meeting is being recorded.
Okay. Yes, welcome to our data mining for this week, first class this week. I've got a handful of announcements of things coming up. So just a reminder of Wednesday, the next class period, you have your quiz on chapter 2. And so the practice problems, again, posted here. It's the true, false problems. The only difference about this quiz and the previous quizzes in this style is that everything's worth double points right here. So still 4 problems, but 2 points for the correct answers, -1 for incorrect answers, 0 for blank answers. And again, that's next class period, Wednesday. Any questions about just the mechanics of the quiz, administrative thing? Yes. And then probably every subsequent quiz will also follow this same point pattern. Yeah. Yes, Jake.
Those of us who are making up last week's quiz at office hours, can we just show up when that undelayed?
Yep, show up anytime. I'll print it out as soon as you arrive, and we need to take it. Okay. Last time I told you all that chapter 3 was going to be the last chapter before the midterm, and I want to shrink the content on the midterm even further than that. So I have announcements here today about this midterm update. Here's the full list of sections that will be on the midterm. So everything from chapter 1, chapter 2, all the stuff that we covered. We skipped 2.3, so 2.1 and 2.2, that's everything that's going to be on the quiz. And then chapter 3 here, I want us to temporarily pause the stuff that we were talking about last time. Last time we talked about, here we go, these linear models, sections 3.1, 3.2, and 3.3, and finished up with a whole bunch of pictures about different loss functions. We are going to get back to that, yeah, there's already a lot of stuff on the midterm here, and so I decided that it would be better to pause this until after the midterm. So the midterm's only going to be on the, I guess in my head, the reason for making this distinction, the midterm's only on the statistical stuff about the machine learning, and the optimization stuff we're not going to have on the midterm. We'll cover that for the final exam. Yeah, couple of reasons why. So we started talking about this. There's still one more note packet about optimization here that we will talk about. But it gets, I don't know, it's different than the statistical stuff. So I want us to be able to focus on the statistical stuff. You all be able to focus on the statistical stuff, and so that's what we'll do. So this is the actual list of sections right here from the textbook that you'll be responsible for. We did cover already this notes-linear.pdf file. That's what we did Wednesday last class. We'll revisit that after the midterm time, and then also talk about this other notes packet here. The only other notes packet, the only notes packet from chapter 3 that'll be on the midterm is this notes features, which we'll start going over today. This is, I think students tend to find this to be a relatively easy compared to the previous set of notes. It's also the most important set of notes possibly in the whole course. So I want to make sure that we just have a lot of time to focus on this and make sure that this is fully understood by everybody. We'll also, again, so the midterm not next week, the week after that. Next week we'll have some in-class review time. And I wanted to make sure we had a little bit of time too to talk more about just general interviewing stuff or oral exam stuff. Any questions about anything administrative? Everybody's disappointed that the midterm's not going to have more material on it? Yep, I see all your sad faces. Okay, well then today we'll be going over this notes features.pdf file. Again, there's printed copies up here in the GitHub repo. It's this file right here that we will be going over. Maybe one other comment too about like the structure of the textbook. So calculus textbooks are all structured the same because again, we've had 400 years for calculus textbook authors to figure out what should be the right order for talking about things about calculus. Machine learning, data mining, not that way, that the people who invented all this stuff, again, it's still alive. If you are interviewing at Facebook, you might be interviewing with the V in VC dimension himself. And so there's just a little bit more, like we haven't fully fleshed out the right order of doing things. And so I'm doing a little experiment here with a different order, see if this ends up being a little bit easier for you all. And last year, I taught this, crammed all of this into the midterm here, all these skip sections, and we'll see if this turns out a little bit better. Okay. So chapter 3.4, nonlinear transformations. I think there's a very clear connection to the stuff that we were talking about in 2.2 and 2.1, and it also makes those things, gives them purpose. There was a lot of, I don't know, abstract math sort of results in those two sections. Maybe hard to see like what's the big picture purpose of why we care about those things. Hopefully this set of notes, this chapter 3.4, will add some more practical applications to that, why we care about all this VC dimension stuff. Okay, so overview here. In this section, we will see how to build what are called nonlinear models out of linear models. So we're going to be doing things that are going to modify this perceptron hypothesis class to do different things. And this will allow us to easily construct models with different VC dimensions that are appropriate for our data sets. And again, different VC dimensions, when you see people talking about different VC dimensions, you should be thinking about that this implies different generalization errors. Because the VC dimension, the thing that it told us, the reason we care about it is it tells us the generalization error. And again, the generalization error is, so I'll do 3 bars right here, is like it's defined to be the E in minus the E out. The in sample error, the thing that we know, versus the out of sample error, the thing that we wish we knew, but there's no way for us to possibly calculate the E out. E out is the thing that we wish we knew. We do know E in, so the generalization error is this difference, and it's our tool to help us figure out what our out of sample error is going to be. About, I think 5 years ago, this picture was created, maybe longer than that, pushing a decade now. And it's making fun of a lot of trends in recent machine learning, data mining stuff, where this is what people used to be like. They used to be talking about their VC dimension of kernel is too high, blah, 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 doing a lot of technical stuff, actually getting good results. And more recently, so this is the old school people, talking about the math behind things. More recent trends with deep learning being that, I don't know, you don't need to maybe know as much stuff to get, I don't know, start up PyTorch and start doing stuff. But their errors are all over the place. People don't know what's going on. And so this set of packets is going to help you, or this set of notes right here is going to help you be like this guy up top, knowing what all those words mean, why we care about them all. And so you'll be like him. You'll be this and not this. Okay. So our first technical thing for today, defining a feature transform. What is a feature transform? How does it relate to the perceptron hypothesis class? The textbook and basically all machine learning literature uses the capital letter phi. This is the Greek letter phi right here, written out PHI, and that's a capital phi. capital phi is our feature transform, and it takes entries in R to the D and maps them in R to the D squiggle. The textbook here uses the D squiggle. That's a tilde on top of the D. I've only ever heard like 90% of people that are machine learning people pronounce this as D squiggle. Occasionally people pronounce it as D tilde, but that's one extra syllable, so D squiggle is what people say. And this is the R to the D right here. This is our, again, the space of input features or input data points. Space of input data points. And this goes by many names over here. It can be the space of features. Or the textbook uses a fancy like Z thing like this to describe this space over here. That's a fairly common thing to do. And another synonym for these feature transforms is this can sometimes be called a feature map. Feature map or a feature function. Transform, function, map, basically all synonyms for each other. Or there's another word that is kernel that is very closely related to these feature transforms. Technically, it has a slightly different shape, but anytime you see the word kernel, you can see, you should think about feature transforms. So at least at this point, we're only going to be using this notation with feature transforms, but you will hear people, you will see documentation in libraries using this word kernel right here. But it's the same thing. Your next homework assignment, so there'll be a homework assignment that we'll talk about on Wednesday, will be related to this, this set of notes here, trying out these different feature transforms, exploring a lot of the different properties about them that we will see mathematically in class today. And in the homework, you will be verifying that those properties do actually play out with experiments on real data. So this feature transform right here gets applied to our data sets. So this space of inputs, again, the X points over here, and we generate some sort of like new X points over here. We could think about applying this feature transform to the data points themselves, but it's often the case that it's simpler to sort of apply it to the hypothesis class. And so right here, I'm going to write H sub phi. This is the notation that the textbook will use for the hypothesis class of perceptrons with the phi feature transform. So hypothesis class of perceptrons with the phi feature transform or feature map or feature function or kernel. And we're going to explore throughout the rest of these notes different versions of these phi functions, seeing what they do. The actual definition here, though, of H sub phi is going to be the set of X mapped on to W. Phi of X like that. We'll need a transpose here, where now W is contained in R to the D tilde instead of R to the D. So it's just basically applying this phi function to all of our data points before sending it into our hypothesis class. We could define similar versions of the this hypothesis class combined with a feature transform on other hypothesis classes that are not the perceptron, so like on the h-axis or h-axis 2 hypothesis class. But for this set of notes, at this point in time, we're just going to stick to the perceptron. One last weird notation-y thing that the textbook does is sometimes, but not always, sometimes they will put tildes on top of the W's over here to indicate that the W is this D tilde, D squiggle dimension instead of the normal D dimension. And sometimes they will say like H squiggle contained in H sub phi like this. And sometimes they will leave off the squiggle. If you see a squiggle, then you definitely know that whatever the thing is you're looking at is related to the feature transform somehow. But if you don't see a squiggle, then it might be about the feature transform. It might not be. You just have to know from context. Any questions about the notation here? Every day we get to introduce like 20 new terms and a whole bunch of new things that are hard to pronounce, like Greek letters and squiggles, and wouldn't be data mining without all of that. Starting off our day, starting off our afternoon with fun new Greek stuff. Okay, this, yeah, hopefully, I don't know, mechanics here of what's going on mostly makes sense. Again, the phi function here is just being applied to the data, somehow transforming it. We're going to explore in the rest of these notes, again, these different phi functions. The first of those, and the most important of those, is called the polynomial feature map, right here. So the next page down here, the polynomial feature map. And it is, so phi sub q, we previously saw q as being like a name for these loss functions. The textbook uses that. It also reuses q here for a reason that I don't understand as being the degree of the polynomial. But q here is the degree of a polynomial. Degree of the polynomial. And the reason this is called a polynomial feature map is because if we have phi sub 2 here, 2 is the degree of our polynomial. We're going to take all of the polynomial combinations of our x1 and x2 and add those as features. So here are our new, this feature map right here. This phi sub 2 goes from r to the 2. Our original data points have just 2 dimensions inside of them. I know that because the x1, x2, not in bold meaning that they are scalars where the index is not which vector we're looking at, but which index in the vector we're looking at. And there's only 2 of these indexes. So this is the x value itself is 2-dimensional with x1 and x2. And this is going to map us into a 5-dimensional thing, 1, 2, 3, 4, 5 right here. That is mapping us into r to the 5th. These extra dimensions, so x1 squared, just taking whatever your first dimension of your data point is, squaring it, x2 squared, taking the second dimension of your data point, squaring it, x1 times x2, the product of those two x1 times x2. The third degree polynomial feature map defined similarly. Now, instead of getting all of the second degree terms, we also calculate all of the third degree terms. So here, these first 5 things are the same. All of that, those 2 things are the same. The new parts in the third degree polynomial, all of these things right here, these are the new parts, where it's now all of the third degree possible combinations of things. So x1 to the cubed, x2 cubed, x1 squared, x2, and x1, x2 squared. That's all the third degree possible combinations of things. The question 1 right here and problem 1, how does this affect, or how does the choice of Q affect our E sub n? Well, my claim here, my first claim is that if we have, say, H of phi sub 2, that is going to be a subset of H of phi sub 3. The reason for that is all of this new stuff over here, these new parts that I underlined in blue. If if those were just like set to 0, basically, then we get the same exact possible results over here. And so adding more features can somehow only gives us more power about what we're allowed to do. And so that's this subset relationship. And we saw before that if one class is a subset of the other, that tells us about the in-sample error of those subsets. And so E in of G phi3, so G phi3 coming from right here, less than or equal to E in of G phi2, like that. And again, the G's, the G for whatever our hypothesis class is, the textbook uses that as the arg min over the H and the big H of our En of the little h's like this. So in this case, with the second and the third degree polynomials, the in-sample error G phi3 is going to be less than or equal to the in-sample error of G phi2. Yes, question?
If we back up, is there a reason why like can't square both multiply each other? Like x1 squared times x2 squared.
So the question is, what about the where is x1 squared x2 squared? And this has 4 different variables inside of it. So this would be what I would call a 4th degree term right here. And so this is not in the 3rd degree feature map. There is a 4th degree polynomial feature map that would contain this term. So here, when we're talking about the polynomial feature map, it's not, say, all of the possibilities where one of these degrees is less than the subscript over here. It's where the sum of all of the exponents up here is less than or equal to that subscript right there. Does that answer your question? Good question. Other questions so far? Okay, so this result right here tells us that using a higher degree polynomial can give us better in-sample error. If we scroll down real quick, I have 2 links down here that we're gonna take a look at, and these links will help us visualize why that's the case. Like what exactly is gonna go on here that's gonna help us give us more power. And so this first link, both of these links are about the polynomial of 2nd degree. And it's a little bit hard to see here, but this circle right here, this is the best possible decision boundary for this problem between red points on the outside of the circle and blue points on the inside of the circle. This is clearly a nonlinear problem, and so the perceptron hypothesis class by itself cannot solve this, that you get a very high in-sample and out-of-sample error on this problem. If we apply the polynomial feature map, though, we are, so it says up here, expanding into a higher dimensional space. What they are going to add right here, the additional term here, so there's now, we started in an XY plane, 2-dimensional data set. Now we're in a 3-dimensional data set, taking up this whole 3-dimensional space here. And the sort of Z component here, the component going upwards, how it's currently rotated, that's the product of x1 times x2. So it's just one of those terms in the 2nd degree polynomial. And in this case, what you can see is that all the blue stuff is now at the bottom down here, and the red stuff is up above. And in this higher dimensional space, there is now this separating hyperplane right here that's able to separate these blues and these reds in this higher dimensional space. So yeah, originally very high in-sample error for a linear hypothesis, but now we have a 0 in-sample error for a linear hypothesis in this higher dimensional space, as long as we construct this higher dimensional space in a clever way. So there's one example right here. And maybe scroll back for a second. So what they're showing now, so this is this circle here through this kind of manifold up here. This is where the hyperplane, the plane in 3D intersects the actual data set. And if we project that down onto back into 2 dimensions, what was a linear separation in the high dimensional space becomes a non-linear separation, this circle right here in the low dimensional space. Other visualization right here. So now we have 2 colors here, red and green, where they're associated in quadrants. We've seen the H multi-axis 3 hypothesis class would do well on this, but the linear hypothesis class, the perceptron hypothesis class, would not do well on this because the data here is not linearly separable. With, again, a polynomial feature map, though, this is the quadratic again. When you square all of these terms, they get projected like this. That negative quadrant over here got projected up. The green quadrant over here got projected down. And now we are in a high dimensional space where things are linearly separable. There's, again, a 3-dimensional space right here, and things are linearly separable in the 3-dimensional space, not linearly separable in the 2-dimensional space. Yes?
Do you know like what the polynomial is?
It's the same polynomial. It's a 2nd-degree polynomial where so in order to make it visualizable, it's they did not use the x1 squared x2 terms, only the x1 times x2 terms. So in both of those visualizations, their 2-dimensional space is x1 comma x2, and their 3rd-dimensional space uses this x1 times x2 right here. So the reason why the x1 times x2 is useful in this second right here is because if you're in either of the green locations, the signs of x1 and x2 will be opposite of each other. So you multiply them together, you get something negative. The signs of the red locations equal to each other, both positive up here, both negative down here. And so when you multiply them together, you get something positive, and they get projected to the same space. Maybe, one of the interesting things that is a takeaway from these visualizations is that these two data sets look very different from each other. This is sometimes called the XOR data set here, this checkerboard pattern, and the circle data set over here looks very different from the XOR data set. If we were trying to construct use our H-axis or any of those hypothesis classes, it would be, we don't have a hypothesis class at this point that can do both of those 2 tasks and get 0 in sample error. But it's somewhat remarkable, somewhat interesting that this same polynomial feature transformation, just x1 times x2, gets good results on both of those very different looking data sets. I don't know if that answered your question somewhere in. Okay. I'll say that, for me, I remember when I first saw those pictures, and I remember feeling a little bit blown away at first that that's something that we could do, and feeling like I understood it, and then immediately feeling like I had no idea what's going on. I said that to a handful of you all throughout this course, that you'll bounce back and forth between fully understand it, fully not understand it many times. But this is one of those things that, for me in particular, I had to see just over and over again before I actually believed that this sort of transformation could work. Any questions so far? Other questions? Okay, in red over here, we stated these facts in the specific case of the second and third degree polynomial. Let's just go ahead and state this in the fully general case for any h of phi sub I, that will be a subset of h phi sub j if and only if I is less than or equal to j. And if that's the case, if I is less than or equal to j, then En of g phi of j guaranteed to be less than or equal to En of g phi I, like that. Question?
Yeah, so when we're having like new polynomials, are we necessarily using every component? Like, for example, P3 or something, are we necessarily using new group parts?
Yeah, this is a good question.
Select any of the ones that you want.
This is a good question. And so the question reworded is that, like, do we have to use all of these terms? Can we use only a subset of these terms? Or how are we deciding which of these terms we're going to be using? And so remember that our hypothesis class is this, so I'll rewrite it here, h phi being the set of x into w tilde transpose phi of x, where w tilde contained in r to the d. And we're still sort of glossing over at this point about how do we select these w tildes in this case, or w in the original case. But if, for example, well, for w tilde here, we have, w tilde has a corresponding entry for every one of these terms up here. And so if we have the 2 degree case, x1, x2, x1 squared, x2 squared, x1, x2, this is our output of phi sub 2 of x equals this. Well, then the w tilde has, again, 5 particular terms right here. We could have, say, 1, 1, 0, 0, 1 for our w tilde. And in that case, because we have zeros here in the corresponding entries of w tilde, the quadratic terms right here, x1 squared, x2 squared, will not actually get used. They'll be sort of ignored in the final classification process. And because of that, this hypothesis class, as I've written it right here, with 5 terms, that still sort of all the logic of these pictures right here with only 3 terms, it still applies to the 5-term version, because you can just, the training process could set zeros here. And that's why also I'm claiming that these are subsets of each other, because the w's here could be equal to 0 for the w's corresponding to the blue part up here. All of those w's could be 0, and in which case our hypothesis class reproduces all the hypotheses from up here. Did that answer your question? Okay. Yeah, good question. Okay, so this is all about the in-sample error that, and it's a very important thing that as our degree increases, we know that our in-sample error is going to go down. Part 2 over here, still related to the in-sample error, talking about the universal approximation property. There are many things in machine learning that have this property. The polynomial feature map is one of them, one of the first things, definitely the first one where it was discovered that it has this property. So what is this property? This property is that when we have the limit as q goes to infinity. Q in this case, because this is the thing that parameterizes our polynomial feature map. The limit as Q goes to infinity, Q again is the degree of the polynomial. As that goes to infinity, our in-sample error En of G sub phi sub Q will equal 0. I say this is definitely the first time that this was discovered, because this was discovered like 300-400-ish years ago with, and you've learned about this in calculus with your Taylor series. That the Taylor series has a handful of other names in calculus too, but if you can approximate basically every interesting function with a polynomial of sufficiently high degree, and as the degree gets high enough, the error term goes to 0. There are some weird functions where this doesn't hold, but every like meaningfully interesting function this holds. In words, again, I'll write it out. What this is saying is that every interesting function can be approximated by a perceptron plus polynomial feature map, poly feature map of sufficiently high degree. This is one of the like standard facts that I just have to know. Any of the machine learning things that have this universal approximation property for like an interview at a company, it would definitely be expected that you know about this universal approximation property. And so for the polynomial feature map right here, one of the most important properties that it has. Both of those two, everything we've talked about so far is about the in-sample error. So if we can get it down to 0, why don't we just make our polynomial feature map always be infinity, make it like as really high as we can, and then we always get really good error. Well, that's why we've been talking about this trade-off between in-sample error and out-of-sample error with the VC dimension and this generalization error. Again, we've had this graph, maybe so there's space, I'll do it right up here. Bottom of page 3, talked about the model complexity as the x-axis, model complexity as the x-axis. Our VC dimension is the only thing that we've seen as model complexity so far. But now for the new hypothesis class of H phi sub q, q is also now another measure of our model complexity. The more complicated polynomials, more complicated models. And we will see that, or we have seen so far, that the in-sample error goes down arbitrarily to infinity. And the generalization error, what we'll see next, is that the generalization error will go up as Q increases. And so there's this balancing act trade-off here of balancing off our generalization error for our E sub in, because our E out is the difference between those two things, and this is the thing that we actually care about. So there's always this balancing act when we're working on a real-world problem about our in-sample error versus our generalization error. Where is the optimal model complexity for us based on the amount of data that we actually have? Wait another second before scrolling down here. What we're going to talk about next is how the generalization error of this polynomial feature map, how Q affects that, by seeing how Q affects the VC dimension. So part 3 right here, the VC dimension of the hypothesis space, H sub phi equals D tilde. What is the formula for D tilde? And thus the VC dimension based on K and D. There is a formula for how many terms are in a polynomial, and it is equal to, let's see, Q plus D, choose Q. So this is that choice notation that you probably have seen before and forgot. I always forget it whenever I don't use it actively. And this is the exact formula for our new VC dimension. D tilde is exactly equal to that. For our purposes, though, we don't really care about the constant factors and things. And so the asymptotic notation is sufficient for us. And this is theta of D raised to the Q power. So conveniently, the polynomial kernel here has a VC dimension that is polynomial in the power Q here of the polynomial. It makes it, I think, fairly easy to remember. This thing in magenta here is the thing that you definitely need to remember. And so this tells us, well, let's see. If we, like, I don't know, sometimes there are machine learning courses that don't talk about the VC dimension. They just talk about model complexity in like a maybe abstract way. And it's obvious that the Q, the degree of this polynomial makes things more complicated. But the fact that we have talked about this VC dimension tells us like exactly how much more complicated our Q value here is going to make our formula. Exactly how much more data are we going to need based on how much we increase the our Q value there. So we have through this like a very strong way of measuring our VC dimension. Strong way of predicting our generalization error. One of the things that the textbook says, which I don't think I've actually said in class yet, is that there's a good rule of thumb where the amount of data points that you need, the amount of data points in should be approximately equal to 10 times the VC dimension. This is a good rule of thumb when you are first just starting out, trying things out to see like, okay, if I have 10,000 data points, what sort of models can I pick? And if I have 10,000 data points, I need my DVC to be 1/10 of that. And so I would have models with complexity up to 1,000, and I could use that to select what degree polynomial makes sense for my application. Again, your homework will explore that sort of thought process in more detail with you actually plugging in numbers and on real data. Question?
This kind of goes back to like jumper stuff, but we originally had like a round of the MH of n is less than or equal to n to the power DVC plus 1. So now do we have is less than or equal to n to the power D to the power Q?
So let's see. So your question is that we previously said something like mh of n less than or equal to n to the dvc plus 1. This is a true statement, but it's unrelated to this statement up here. This is a statement that is always true for everything. The statement up here, this is our like a rule of thumb for like given some particular data set, how do we pick a model about like what should the appropriate VC dimension is? So given a data set, how to pick a model. And this is just a rule of thumb. This rule of thumb comes from the generalization error bound of the En minus E out is O of square root dVc over N plus a bunch of other terms. And the constant factors here, again, super large, so we don't really care about them. But in order to have sort of like a reasonable generalization error over here, if this thing over here, dVc divided by N, is equal to like 1/10, then we'll get a reasonable sort of generalization error over here. But this is just a rule of thumb. It's not like a thing that's true.
Could you scroll up a bit more?
This.
Where does K come in? I think?
K, I'm not seeing a K.
Yeah.
There's a K in the question. That K is supposed to be a Q, sorry. That's the degree of the polynomial. Go ahead, Kevin.
Yeah, how does B tilde relate to the number of elements in the polynomial feature map?
It's a good question. So D tilde is that number of elements. They're the same thing. So I'm going to scroll out. I'll scroll back down here in a minute. But in general, the phi feature map, for any phi feature map, D tilde is our output number of dimensions. And in this case, specialized to the polynomial case, the number of polynomial terms of that degree is what D tilde is equal to. So here, when this part right here, D tilde equals all this, this is saying there are this many terms in a polynomial of size Q with dimension D, a polynomial raised to the Q power of dimension D, and that's equal to theta of D to the Q. This is our output feature dimension right here after applying the polynomial feature map. Jay.
I was really this question about that, I didn't quite
Sure.
parse out what is the relationship degree on the
So D here is the dimensions of the original data. D always somehow relating to dimensions. It doesn't have a squiggle on it, so it's the original data dimensions right here. In our examples up here, the D is 2 because there's only 2 dimensions in the original data set. The phi function here maps from R2 onto something. So the original D value here is 2. The Q value is the subscript of the phi. So Q here being 2, Q here being 3 is the total number of like what the exponents up over here should add up to. So x1 raised to the first power, x2 raised to the second power. There's a third degree term right here. And so we're allowed to have third degree terms in phi sub 3, but not fourth degree terms. So the Q here is the power that we're raising things to, and the D here without the squiggle is the dimensions of our original data set, and then this D with the squiggle is the output dimensions of our new data set. If you were to say plug in your into Python or whatever calculator you like to use, this choice formula up here, you should see that the size of the result of this formula matches the size of those equations up above. But again, the choice formula here, less important than the final D to the K, D to the Q theta bound right here. That answer your question?
How do we get into the runtime?
There's nothing runtime land here. So here we're using the asymptotic notation, not because it's runtime, but because we have a formula over here, and this is just the bound on this formula over here. But yeah, all of this is statistical stuff, no runtime land. So part 4 here, when would we want to use the polynomial kernel? Let's say we have done some experiments and we have observed that our EN here is relatively high. For our original model, so we'll say for the perceptron. But we think our generalization error is low. And we might think our generalization error is low because we measure EN minus E test. And this value right here is small. And so this tells me that like I need more flexibility in my model because I'm just not able to fit the original training data here very well, but I still have enough data to support the more flexibility. These terms of high, large, small, intentionally vague. There's no like good rules of thumb or what you have to do in order to qualify for this. But if it feels like your in-sample error is high, then the polynomial kernel is likely a good thing to try. Coming over here, like the in-sample error on these data sets here, the circle data set or the XOR data set, the in-sample error here, very, very high. And so that's a good time to use the polynomial kernel. Okay. The opposite situation is when our in-sample error is low, but our generalization error is high. In that situation, we would not want to use the polynomial kernel. We would want to use some other feature map. And again, I go back and forth between saying kernel and feature map. They're not technically identically the same thing, but they are basically the same thing. And so everybody uses them interchangeably. Problem 2 over here is about a dimensionality reduction technique. The previous kernel, previous feature map expanded our dimension. This feature map will shrink our dimension. It's using the PCA feature map or the PCA kernel, and it's defined something like this. You've seen a feature map that looks very similar to this before in your last coding assignment. Here, again, this A matrix is what's doing the transformation for us. Its shape is D by D squiggle, and it converts this X vector down into something smaller. The details about how it converts that aren't going to matter for statistical purposes, but what it does if you're using the PCA in particular is that it creates this new matrix X transpose X and calculates the top eigenvectors of this new matrix X transpose X. There's a note right here that's going to take us to a cool picture of what these eigenvectors look like. I'll come right over here. This, so what I'm looking at right now is just following the link right here on the scikit-learn webpage. They're doing a task where they're trying to predict, if you're given a picture of somebody's face, who does that belong to? And there's a fairly famous data set of different politicians from the early 2000s. And so you got a lot of President Bush here and other people from that time period. And if we scroll down here, these are what the top eigenvectors of that data set looks like. You can see that they look vaguely like face-ish things, but they have certain, I don't know, things about them that are emphasized. So the eigenface 0 right here, if you have a white politician like President Bush, this is going to have a very high value in eigenface 0. But if you have a black politician, like I think Colin Powell, yeah, there's Colin Powell right there, he's going to have a negative value for his eigenface 0 component. And so just knowing this eigenface 0 component of those two people, you can predict with pretty good accuracy whether it's a picture of, say, President Bush or General Colin Powell. Then there's other features about like whether somebody's smiling or things about how their heads are rotated, different things. But these are all the eigenvectors, what the eigenvectors happen to look like on this data set. The important thing, though, from a statistical perspective, how we're constructing this A matrix, what this A matrix is actually doing, doesn't matter. The thing that matters is what our final output dimension is going to be. And so that's what the questions down here are focusing on. So part one right here, again, for every one of these phi functions, we're starting at r to the d, and we're going into r to the d tilde like this. And in this case, we're assuming that our d tilde is smaller than d. So d tilde smaller than d. And so our E sub n will go down as d, our E sub n will go up as d tilde goes down. That if our d tilde has only one feature inside of it, so one of these faces that we're looking at, like eigenface 0 right here, only basically trying to figure out, does the person have light or dark skin tone, measuring their skin tone. There's not a whole lot of information for us to work with, and so we would not expect to get a very great in-sample error. As the dimension of our data goes down, the in-sample error going up. But from a VC dimension perspective, as the VC dimension here, the VC dimension is now going to be exactly equal to d tilde. In fact, the VC dimension up above is also exactly equal to d tilde, but here d tilde is something that we're specifying directly by whatever the size of the A matrix is. Up above, we specify d tilde indirectly by specifying the Q value, the degree of the polynomial, and computed d tilde from that. But our VC dimension always theta of d tilde. And so as d tilde goes down, then we know that our generalization error will also go down. The size of the model here, the VC dimension of that model is proportional to our generalization error. So making this smaller makes our generalization error go smaller. So again, we have this trade-off here about making d tilde go down. Decreasing our output dimensions is going to make our in-sample error worse, but our generalization error better. And picking the optimal d tilde, the optimal number of these features down here. Again, d tilde is the number of these eigenface features that we're using on this problem. Is a balancing act to balance our in-sample versus our out-of-sample error. Any questions on this PCA feature map? Everybody's an expert on it, it's also obvious. Again, your next programming assignment will have you working with these, selecting different values, seeing how things change. So that will hopefully help make things a little bit more concrete. Question? Yes.
Yeah. How do you define d tilde?
Sorry, how do you define what?
D tilde.
Question is, where does d tilde come from? And in this case, for the PCA, d tilde is a hyperparameter, so specified by the user. For the polynomial up above, the hyperparameter Q is the hyperparameter, and indirectly d tilde determined by Q. So up above, you don't get to exactly specify what d tilde you want. You just can specify your q, 1, 2, 3, 4, 5, 6, 7, 8, 9, some integer like that. And so there's a limited number of d tilde possibilities. Down here for the PCA, this is something that you just decide in advance based on whatever other knowledge you have. Like you've tried it without a feature map and you had a really great in-sample error, like 0, but your test error was really high. And that tells you that the PCA feature map would be something good to use with a small d tilde value here. But the straightforward answer to the question is that it's just a hyperparameter specified by the user in advance. Okay.
When we were reducing the dimensions of this homework, was that an example of PCA or not?
Yeah, it's a good question. So we've already done one of these dimensionality reduction problems that was not the PCA. I listed the PCA one here first because this is mentioned in the textbook. But the next problem down here is the one that you did before, not mentioned in the textbook. It is this random feature maps, where A was set randomly instead of set according to the eigenvectors. Only difference between this and PCA. Difference is how A is calculated. That in the PCA, there's a complex formula for it. In problem 3 right here, it's all random. Problem 3 right here, this is what you actually did on your previous homework. This is the previous homework. And actually, in practice, nobody uses the PCA. It turns out that it makes really cool looking pictures like this for the features, but it does not give you good results. It does not give good in-sample errors. But these random features actually do give you good in-sample errors. There's a famous machine learning model called the random kitchen sink, which is the perceptron hypothesis class with this feature mapping right here. The random kitchen sink is currently today, like October 21st, 2024, state of the art for a very, very large number of problems in the machine learning world. It was invented in 2006 by accident. The guy who invented it, I have his picture right here. This is what he looks like. And there's a presentation of him describing how he invented it on accident. He describes how it was an accident. He thought it was going to be a really bad thing to do, totally stupid thing to do. And it turned out to work incredibly, incredibly well. And in 2017, he was given a special award called the Test of Time Award at the biggest conference in machine learning for this contribution right here. His actual presentation, I think, is very accessible. If you're, I'll just say I'd recommend that people watch this YouTube link right here. Goes to the presentation where he talks about the random kitchen sink, why he thinks it works well, and how he accidentally invented it, and so on. It's very accessible. You definitely know everything at this point to be able to follow along with what he's saying. But yeah, state-of-the-art thing, works better than deep learning, works better than ChatGPT, works better than neural networks on a very large number of problems today as we speak. So why is that the case? For all the same reasons that we just talked about with the PCA, that as your EN, so how does EN vary with D tilde? As D tilde goes down, EN will also, or will go up, but it turns out not very much. That's the surprising part, that it seems like if you just have totally random features and you only have a very small number of them, that you should have a very high in-sample error. but it turns out that you do not have a very high in-sample error. And then how does EN for random features compare to the EN for PCA? Say EN of G random, typically much less than EN for G of PCA. We can't actually say that this is always true, not guaranteed to be always true, because neither of these are subsets of the other. Not guaranteed to be always true. But there is actually a moderately complicated mathematical theory that says that it is true with high probability. We won't get into the theory about why that's the case, but it happens to be the case that it's true with high probability. And so people, I don't want to say people who don't know what they're talking about, but people who are not experts in machine learning often talk about using PCA to do things, but people who are experts in machine learning use the random feature map and get better results. That's part 2. Part 3, what's the VC dimension if D is less than or equal to D? So this is the same sort of stuff we talked about up above, that the dVC is exactly equal to d bar plus 1 equals theta of d. The reason why, or not d bar, d squiggle plus 1, the reason why it's d squiggle plus 1 is that the VC dimension of the perceptron is 1 plus the ambient dimension. We basically never care about that, but I happened to write it out right there. So I explained it. The thing that we care about is the theta d right here. That's the theta d squiggle right there. That's our VC dimension if d squiggle is less than or equal to d. It turns out that this can only be used for reducing our dimensionality, cannot be used for increasing the dimensionality like the polynomial kernel can. So even if d squiggle is greater than d, the dVC remains theta d. And intentionally no squiggle, not a typo. No squiggle. So you cannot use the random kitchen sink, the random feature map, in order to increase your number of dimensions. In order to increase your VC dimension beyond what it already is, you can only use it to shrink your VC dimension. Let's see, I think there's one last. So under what conditions would you want to use the random feature map or PCA? So there's a lot of advantages of the random feature map over PCA. Actually, before talking about the differences between them, I wanted to talk about the why to use either of them. If your EN is very small already, and your generalization error EN minus E out is very large, then those two things together imply we should shrink the dVC, and either random feature map or PCA is a good way to do that. In practice, if I was really trying to get the best possible error, I would try both of them and just see which one happens to give the best results. But if I could only pick one of those, so if it's possible to try both, then do it. If not, then I would personally always pick the random feature map. We already talked a little bit about the EN is usually better. But one other thing that we haven't talked about yet is computation. The random feature map is just much, much faster to compute. Much faster. The computing A in PCA, computing the A matrix in PCA. We talked about this a long time ago that, again, the PCA is defined as the top K or the top D tilde eigenvectors, and that takes time O of D tilde times D squared. So D squared here being the ambient dimension. Ambient, another like synonym for the original, ambient, original dimension. And the D squiggle here being the new dimension of the space. Modern machine learning problems have D on the order of like billions, pretty common. So this is an expensive thing to do. Any questions? Yeah, Ty. Yeah, that's a good question. Is there a specific probability distribution that it makes sense to generate A from here? And it turns out that it really doesn't matter what probability distribution you choose. That the results for this thing right here hold for essentially any probability distribution. And so the thing that is the most cool thing to do is to randomly just use either like +1 or 0 as the most strict possible filtering things down. If you're not using that, then like just uniform distribution over -1 to 1 or Gaussian distribution, standard things to do. But it basically doesn't matter. You tend to get good results no matter what. Let's see, that's pretty much all of our time for today. So if anybody has more questions, I'll stick around and get those answered. Otherwise, we have a quiz on Wednesday, and I will see you on Wednesday.